All right. Yeah, good afternoon. Thank you, Mr. Chairman, and I'd like to thank the organizer for having me here. So, yeah, my name is Zhigang Chen. I'm from Nankai University, which is in Tianjin, a city about 2 hours from Beijing, the capital. So I'm going to talk about some of our work on photonic lattices for topological control of light. It's not really the material per se, but hopefully the concept, the idea can help for the structured design, can be useful also for this community. All right, let's see. Okay. All right, yeah. So what is the motivation? The motivation starts just from this familiar Kagome lattice, like say in the Japanese basket, right? So hopefully I can show you that in this simple structure, inspired structured design can be used as a very powerful platform to explore intriguing physics and also for advanced photonic devices. So you will hear me talk about the geometry design, the lattice design, and underlying band structure, band engineering leads to topological control of light and go to device and application. So this is the outline. Mainly I will talk about 4 parts. Okay. So the first part will be in the fundamental Kagome structure, maybe with a slight deviation of the unit field, and then go to, sorry, let me see, go back. Yeah. So Kagome lattice is the basic structure, then go to super honeycomb lattice, then fractal structure, then disclination lattice. So you hear me talk about some of the concepts, such as subsymmetry and generalized total angular momentum, pseudo-spin, angular momentum topological transport, and the protection, exponential scaling, and the vortex devices. So before I go to part 1, I'd just like to give a very brief introduction of topological photonics. We know that light field manipulation, or structured light in general, and topological photonics are 2 crossing frontier in the photonics area, right? So why you need a topology? Because it gives you a new degree of freedom to control or manipulate light, right? It can also lead to a new aspect for the next generation photonic devices. Here's an example. Topological lasers, right, which is currently investigated around the world. So why we need a topological laser? Very basic thing here is it can have robust, not just a single laser, can have an array of lasers. It has a useful application, go to say facial recognition, autonomous driving, optic communication, and laser sensing. Very dependent on these laser devices, right? So probably for this laser pointer, it will not make a difference. But if you go to advanced application, the laser thinner, the single mode quality, everything is important. So that's the underlying driving for this research here. Okay, yeah, this is a very brief slide, just to show you that from the mass to condensed matter physics, right? We know that the topological band theory has led to many discoveries, including, say, topological insulator and wire semimeter, right? So what I want to mention here, it is the same Nobel laureate, Zhigang, and his colleague, Rahul, brought this concept in photonics. They first asked, can we use topology or quantum Hall effect to create unidirectional propagation of light? And this soon led to the pioneer experiment from Marion Soji's group, including Yidong Wang and Richmond and Alex Zermatt for Montesquieu's group. So then the pioneer experiment opened the field of topological photonics. So, but you can see here, I'm emphasizing this, the bed theory. So the topology we're talking about is not about the vortex, not or link. This is a real space structure. It's really talk about the momentum space, the topology of what? Of the Bloch wave singularity or Bloch wave in the K space. So then you will need the periodic structure, right? Just like in solid state. So there are many research going on around the world using different platforms. So here, our focus, I will just talk about the photonic lattices which we used, okay? So starting from the basic, very simple honeycomb lattices, right? Going to say more complicated like Lieb lattice or T-graphene structure to Kagome, super honeycomb, and a fractal. And this is the thing I'm going to talk about. So just in case you're wondering how we make this lattice, we do not rely on advanced fabrication. Really, very simple. You can use just a CW laser to do optic induction, to write the waveguide in the nonlinear crystal one by one. Okay. Of course, it has limitation because the propagation distance, also the spacing. You can also use a femtosecond laser right in the silicon glass. So both technique we can use. If we need longer sample, longer propagation, we use femtosecond laser writing. But if we need nonlinearity, right? So we just use nonlinear crystal, use CW laser to write one by one, write the waveguide. So what you see here, just sorry. What you see here is actually the transverse is the output, like say XY. Each dot here is a waveguide propagate along Z. Okay? So it's not the matter surface. You can see it's a matter structure created in a three-dimensional structure. It's a waveguide array. Okay. So based on this, we use this photonic lattices to study, say, graphene topology, topological singularity mapping, which I'm going to talk about, topological edge state, right? Flat band localization, and also the nonlinear control topological state, like I said, because we can induce this waveguide in a nonlinear crystal, so we can really study nonlinear behavior, how to manipulate control the topological state, including like this science paper we published here is the first time we actually developed non-Hermitian topological state, but use local nonlinearity control the global symmetry of the system. Okay. Okay, now go back to the topic today. The first part is the Kagome lattice. So apart from this Japanese, basket, the key word here when we go to the physics is the flat band. It's the flat band. So the flat band is a complete dispersionless energy band, right? Because the electron bounded in the flat band, it has strong, interaction. So this leads to many behavior of strongly correlated many-body physics, right? Just one slide here to show that if you open the literature, you'll see how many research based on this Kagome lattice. So here I say it's actually an inexhaustible golden vein of intriguing physics, which is true, not just in condensed matter, in material science, in photonics, right? So an example here from the condensed matter, you can start from the superconductivity, quantum spin liquid state, anomaly quantum Hall effect, fractional Chen insulator. And this all related to the flat band phenomena or flat band localization responsible for explaining the physics behind it. So this is the reason why it is attracting a broad interest of the scientific community. So like I said, there are many research, even in photonics, in different groups. So here, I only focus on the research example I'm going to show you is the research from my group. So the one example here is what's called the unconventional flat band or loop state. So this starts from Bergman in 2008. He has a theory paper, say, we know in the flat band lattice, you can have this compact localized state because distract interference. So they form a compact, only occupy a few sites, right? So then if you put this compact localized state, like 2D structure, you wrap around to become torus. You count the number of state. There's always state missing. The missing state are this what is called a non-contract loop state. Okay, in this direction or here. This corresponds in the original Bergman's paper is an infinity line state. But you cannot really experiment easily to fabricate a three-dimensional structure to realize this. So we came up with the idea here is use a Kagome lattice, right, a Kagome ribbon, and wrap around, right, and then to create such a structure. This structure will be able to satisfy the boundary condition, called continuous boundary condition, in this radial direction. Oh, sorry, not the azimuthal direction, right? So we observed this localized state. So this is the structure, the Kagome lattice structure. This is the loop state. By the way, this structure, of course, it's not we created this. People also use this Corbino structure used in the metamaterial as a nanophotonics, okay, because this particular boundary condition. Okay, so this just shows you that by writing the waveguide one by one, we can create such a structure. So here's another example. It's related to topology. We all know when you have this topological edge state, it has what is called a bulk boundary correspondence. Okay, so traditionally, what you need is that you need the whole structure has the symmetry, so it has a topological invariant, right? And then it can convert directly to the boundary state. Okay. But the research has also shown that there are some, even you have the topological invariant, you don't have the boundary state. And here, what it shows is that even you do not have the overall symmetry or overall topological invariant, you can also have edge state. Right? So this is the concept we call the subsymmetry. It's very simple. Use this illustration here. That's the global symmetry. This is the subsymmetry. Part of the system has the symmetry. So again, based on this Kagome lattice, we were able to demonstrate this high-order corner state, which satisfied the subsymmetry, prove the concept of subsymmetry. It's actually, if you look at this here, this is the Kagome structure. When you have the subsymmetry idea, this is very counterintuitive. So this, again, we already show you, this is the lattice, we established by, CW laser writing. Then A side, the corner side, is the one you excite for the corner state, right? But also, we use additional bridge here. This bridge introduces long-range coupling in this side. So when you have the subsymmetry, the state we're pin at the corner protected. It will not, even this bridge, you move closer, light will not go through it. Okay? But when you break the symmetry, even so if you have the symmetry, you put the bridge closer, you will not go. When you break the symmetry, even you put far away the bridge, light will go to that bridge. So this is proving that we do have this subsymmetry protection. By the way, the work, and much of the work here is collaborate with my theory collaborator, Professor Hiro Bulian from University of Zagreb in Croatia, and Roberta Merendotti from INRIS in Canada. Okay, so here's another example. This is the work recently just published in eLight. Okay, this is showing a new state, what we call the multi-topological phase. And traditionally, we say each system, when you have an overall topological invariant, you will have one set of boundary state. But we can see there's a system that you can have multiple a topological environment which corresponds to multiple boundary state. Okay, of course, there's underlying physics involved here. It's what is called you need the interstellar coupling have some constraint. Okay, for this I will not go to the detail. If you're interested, I just show you that again. We use this, Kagome structure with the distortion of the unit theory. You can demonstrate that there is such a multi-topological phases which can be explained by the theory we developed. Yeah, maybe I will spend a bit of time on this one. This is a very interesting thing, is like you have a discrete system, how to understand the total angular momentum conservation. When you have the graphene structure, it is a Dirac cone here, so it's a linear band dispersion. Then we write total angular momentum. This has already been proved. In the Z component, you have the total angular momentum equal to angular momentum of light plus the pseudo speed of the structure. I will explain later. But when you have such a structure with a quadratic band touching, this simple formula will not satisfy. You have to put the 2 here, and this 2 corresponds to one number here. Okay, so experimentally, how do you verify it? You can see again, Kagome lattice is a good example. Why? Because it has a Dirac point here at the K point. It also has a quadratic band touching at the gamma point. One lattice has different topological singularity, or called high symmetry point, right? So what we demonstrate here is the question we want to ask, can a generalized form of angular momentum conservation exist for high order nonlinear band touching point beyond the Dirac paradigm, right? So that's the question. And the answer is yes. This is what is called generalized total angular momentum. The Z component equal to LZ plus omega, or W. SZ is the pseudo spin, and W is the Wandel number. You see, when you have a Wandel number, it means it has a topological origin of this. Okay? So if you define this way, then the angular momentum will commute with the Hamiltonian. So this proves that the Z component is conserved. So the paper just published in PIR. So here shows the experimental demonstration. Because of this, if you excite in pseudo spin half with just the charge 1, you can create charge 3 here. Okay. If you excite with -1, you can create it with -3. So this everything here is by analyze the pseudo spin component. The Z component of this total angular momentum is going to be constant. That means before you do the excitation and after you do the excitation, then this total Z component is conserved. Unfortunately, I will not go through the underlying theory in detail, so because of the time. Okay, so the next one, I'm going to talk about the superhonical lattice. So what's the keyword here? You see, again, this guy has a Dirac point and also another one with the flat band here, right? So this Dirac point here is the pseudo spin half. This one is the pseudo spin 1. It's a 3-band structure. So this is a system with coexisting half and integer pseudo spin. So, okay, this one, again, some of the example I'm going to show you quickly. We can use the superhonical structure to demonstrate what is called the second order photonic square root topology insulator. And high order topology insulator has already been established here, which I'm not going to go through detail. But here is the structure from particularly to the superhonical lattice, right? Because you can see it has a spin 1 and a spin half, right? So if you write it to the Hamiltonian, you actually find that it's very interesting. This structure, the Hamiltonian, you can say, is the product of a honeycomb lattice and a cubic lattice plus a square root. That's why I gave the name called the square root topological insulator. So this cartoon can show that, okay, you can see in some way the superhonical lattice is like, the daughter lattice of the Kagome and the honeycomb lattice. So just with this in the structure, we can also demonstrate and verify that there is a square root high order corner state there. This is the line state I talked about, the real state winding, right? You can also demonstrate in this structure. The unique to this structure is this line state is not going to be really a line, but actually zigzag to fit this lattice. Okay, so this is the non-trivial loop state because the real space topology or the drop point protection. Yeah, I will explain more on this. So this structure here give you an idea. Is if you have the same structure, you can excite something like a Gaussian beam without angular momentum. But depends on where you excite, you can create increase of topological charge. Increase step by step one, say from 1, 2, 3, or you can go to increase by step 2 charge. Like here is 1, here is 2, right? The reason behind this is very simple because you have a pseudo spin half and pseudo spin 1 here. Okay, so it depends on where you excite it, then the charge conversion is different. So we call this dual channel angular momentum vortex ladder. So I don't know how much time I have. I will try to go explain this a little bit. So in 2015, we started with this, we call the photonical graphing. We found that by excite topological singularity, you can transform angular momentum. Okay, so this is called we all heard about spin angular momentum conservation, right? So this is the pseudo-spin angular momentum conservation. Okay, actually we first verify that pseudo-spin is not just for theoretic elegance. It really has the angular momentum. When you map from the momentum space to real space, it gives you a vortex. Just want to mention that 10 years later, a group from China in Shaanxi University, they demonstrate this in the quantum, called quantized vortex in the atomic BEC. Okay, but use the same concept by exciting this, converging, and the drop point have this pseudo-spin mapping. So, of course, we have other research work here later on with Hilbert-Boolean. We developed a theory for the universal mapping from momentum to real space. And then we have this vortex ladder generation by what do they call the Sisyphus pumping. It actually has a several group. Sorry, what is this? Yeah, not just our group, like so from Australian group, another German and Korean dance group. So there's research activity along this. Yeah, so the idea about idea about this Sisyphus pumping, I will show you here, is if you excite, say, the pseudo-spin corresponds to sublattice degree freedom. If you excite the sublattice A, then you will have sublattice B generate angular momentum. But that's just a one-time converging, right? So what is showing here is once you have this convergence done, if you somehow change your sublattice A to sublattice B, then you will have continue another generation. Each singularity mapping leads to generation angular momentum. So this is why you have this stepwise generation, or called cascaded angular momentum generation. Okay, we give a name called the Sisyphus pumping. It's really just like in the laser cooling, you're trying to, excite atom to the high energy state, then when they go down, you do it again, right? But here we do not really have the mass. So it's the tone, it's the analogy between the optics and this condensed matter, really laser cooling. So, so this here gives you the idea or concept about this angular momentum generation. When you have the pseudo-spin flipping, you do this mapping, you change it, and then you do another changing, so you can see you have, even if your input has no angular momentum, you have 1, 2, 3, 4, cascaded generation. okay, we demonstrate in a bulky crystal, but the idea could be applied to nanophotonics, right? Because you do not really have the manual shift. You can do on-site modulation. You can do other trick here to demonstrate this effect. That's I already showed you, particular to this super honeycomb lattice, which is related to Kagome, is because you have this pseudo spin 1 excitation and a pseudo spin half excitation, give you two different channels. Okay. How much time I have? Oh, okay, so I have to rush. So let me just explain briefly what about the fractal. This is our recent work just published in Nature Communication. So we know when you have a real fractal structure, right, you do not have the periodicity. So the traditional or conventional Bloch edge correspondence band theory will not apply. So what we did here is, okay, use the fractal as a unit theory and then construct the lattice structure called a fractal-like structure. And this is first generation. Again, the first generation is the Kagome lattice. So okay. So just this illustration here get you the idea. What about this fractal lattice, right? The tree fractal structure here is very difficult. People walking here try to find this, how to demonstrate the fractal topology insulator. But here, we were trying to study interplay between periodicity, fractality, and topology. What we find is that the topological state here will grow exponentially. Exponential scaling happens in many different fields, even in economics. Here we show that topological state or band gap, mini gap, can go exponentially with this generation of this. This is the paper. Yeah, so there you can see there's one dimension is the curve, is the Koch curve. A two-dimensional is Shipkin-Kiskin gasket form such a structure. So that's what you can see here. The topological mini gap goes exponentially in both 1D and 2D case. Okay, and the number state here related to is linearly proportionate to the topological gap, so also goes exponentially. And here is the experimental demonstration. That's the theory here, which due to time I will not be able to explain. Okay, the last one here briefly about the disclination. So this is the real one we hope not only just to do fundamental research here suffice, right, but it also leads towards the application. So the keywords here is topology and angular momentum. By topological design the structure, you generate angular momentum, and then hopefully to lead to this vortex guide and the vortex laser structure. The idea here actually is to try to use this, momentum space and real space topological protection, we call it dual protection, to create topologic guidance and topological vortex laser. Because of time, I will not able to go through to explain detail, but the keywords here that if you only have the momentum space protection, it's not going to work. If you really have the real space protection, it's also not going to work. Momentum space protection is easy to understand. It's a topological band gap. You need to find a zero mode or zero vortex mode right in the middle of the gap, right? You have to find that. But real space protection is a little bit of a challenge. I will not have the time. Roughly, it's not any vortex can match any rotational symmetry. You need to have a relation that total angular momentum matching the rotational symmetry of the lattice. Okay, so this is just an illustration show you that when it's guided versus it's not guided or divergent vortex. Yeah, like I said, I'm going to skip this symmetry here, the theory, just show you the results, right? When you have this disclination structure is based on the two-dimensional SSH with that disclination cone in the center. And you can see the input, diffraction, and the guided. Those are the results here, which show that you have why this work is important? Because the vortex, we all know, if you do this communication or multiplexing, whether it's the classical quantum regime, the vortex propagate from one place to another place, right? How can keep it robust, or conserve the angular momentum? It's a challenge, right? So this here shows a way to do that. Even you go to a higher topological charge, like here showing that a charge 3, it can be created in the C5 symmetry topological disclination, so long you satisfy burst protection principle. Yeah, let me see whether I can play this. This is a movie. Okay, you can show. Yeah, so you can see here's the difference. If you send a charge 5 vortex, the input division, this vortex is going to diverge dramatically, crazy, right? So, but if you send this to topological disconnection defect, it's like you have vortex guide. They can remain guided, the intensity profile remain a single donut in there, but also the singularity stays there. So that's the angular momentum transport by topological principle. Yeah, I'm going to the end of this. So the application was mentioned that we hope to have the advanced photonic functionality. So one thing you can have in mind is that you can have a vortex topological crystal fiber, photonic crystal fiber by topological disclination. People have been working on this, trying to use photonic crystal fiber design, right? Here shows one possibility is the topological approach. Not only that, we're also working that without, say, just sending vortex, but use a nonlinear mechanism to have the structured general vortex, then get the topological protected transported from the fiber. So the topological disconnection-based vortex fiber. The other thing we're working on is the VCSEL, topological VCSEL. Of course, by semiconductor structure, it's very difficult, it's fixed. So we're using soft matter to make it flexible, and also by using this perovskite material combined with the color liquid crystal, have the cavity with this topological protected vortex. You can have a real vortex laser with topological protection. That's the plan. Okay, the take-home message, as I already explained here, is that we hope that starting from a simple geometry, you can have inspired topological structure, which can lead to multiple research directions to explore fundamental physics, but really can uncover unconventional applications. Okay, with that, I would like to thank my group and also my postdoc, my collaborator, and thank you for your kind attention.
Thank you very much. Thank you very much for the talk. Very interesting. We have just a few for 1 or 2 question marks. So, yes?
You mentioned specifically the Sisyphus effect. If I understand it correctly, Sisyphus effect involves loss of energy. But if I understand you, you mean there is flip-flopping from one state of matter to another. Is that right?
Yes. So okay. I know I actually explained this. I mean, some of them, my challenge is constant. I only explain, it's like a knowledge. It's not, we don't have the mass here, right?
Right.
It's not like atom. You go there, you go down, you know, to do this. But it's the state. We excited, you're coming down, and then excited, you're coming down.
And it's cyclical. It keeps going all the way?
Yeah.
Thank you.
Yeah.
Okay, thank you. Thank you very much. One more quick question, is anyone? If not, for the time of interest, yes? No? Okay, we move to the next talk. Thank you. Let's just thank our speaker again. Thank you very much.